Hey everyone, welcome to Chapter 11, where we are going to be taking a look at sampling distributions. One of the first things that we want to talk about as we're talking about sampling distributions is the difference between mu, the Greek letter, and x bar. Really the big difference, both of these things are talking about average, all right, or mean in some cases, however you want to talk about it. But the difference is whether or not you're talking about the average of a population or the average of a sample. So keep in mind that here is a population. Population is everybody in the United States. That's our population. Okay, so this is everyone in the US. All right, a sample is going to be just a small group of those people. All right, so it's a subset of it. So here's a sample. All right, a lot of times we talk about samples as being an SRS, a simple random sample. So when we talk about mu, we might say the average height of all the people in a population, whereas x bar is going to be the average height of a sample of the population. Okay, so a couple things that the book does, and one of them I really like, is that we talk about mu. Mu is a parameter, and parameters go along with population. All right, it's a measure, or it's an average of the entire population. X bar is a statistic. And a statistic goes along with a sample. And they kind of just point out the P's, parameters and populations, statistics and samples. All right, and so it's really, it's almost impossible for us in all cases to measure an entire population. So we usually use samples to represent that. But obviously using a sample of a population isn't always going to be horribly accurate. So as an example of that, I am going to basically use a small group of numbers. So I'm going to use the numbers that are in your textbook. Where are they? That talk about DMS. All right. So here is the numbers for DMS. It has something to do with smell. What levels people could smell. So let's just assume that these numbers are the entire population: 28, 40, 28, 33, 20, 31, 29, 27, 17, 21. All right, this is, let's assume that's not, but let's just assume that this is the entire population. I don't know what it is. Maybe it's the ages of the people in your office, so the average age of all the people in your office. Well, let's just go with that because that makes more sense. So average age in office. All right, so you're at a business and it looks like it's a relatively young business. Here's the average, or here's the age, not even average, this is the age of the people in the office, all 10 of them. All right, so I'm going to take and put this stuff into Google Sheets for a second so that we can calculate a few of these things. All right, so we got this here, and we'll throw the numbers in. 28, 40, 28, 33, 20, 31, 29, 27, 17, 21. Those are my 10 numbers. All right, so let's just see what is the average of this. Average of these numbers is 27.4. All right. This is the average mu. That's the average of the entire population. When I take a sample of mu and I use an average, especially if I do a single random sample. So I'm going to use table B, and I'll put these numbers up here in just a second. I'm going to use table B in our book, and I believe I have a printout of table B so that I don't have to actually find it, because I can never find it. Here it is. I'm going to use table B, and I'm going to start at line 114 because that's the number that I have here. So line 114 in table B has these numbers. I'm just going to write down a bunch of them because I'm probably going to use them later. So 114, 45149. All right, so this is line 114 as I take a look at that. So just so that we see, first of all, one of the things that happens as we take a look at this is called is what's known as the law of large numbers. And it basically says that as you get more and more data from a population, all right, as the number of observations increase, the X bar of the observed value gets closer to the mean. So X bar gets closer to the mean, or mu, as the number of observations increase. Now that should make sense. If I want to know the average height of WLC students, the more students I ask, the closer it approaches. So let's see what happens with these numbers, and they kind of outline this in the book with the numbers that you have here. So let me grab my Google Sheet here. Oh, that's not my Google Sheet. So let's just take a look at something for a second and take a look at the average. So I'm going to say here's the average of A1 to A1. All right, here's the average of A1 to A2. I'm going to copy that because I'm going to use it over and over again. Here's the average of A1 to A3. I don't know why it's giving me an error each time. I'm basically going through here and if you take a look, I did the average of the first number, the average of the first two numbers, the average of the first three, the first four, the first five, the first 6, 7, 8, 9, 10, until I got down to the average of all 10. You'll notice as I got there, it's 27.4. All they did with this was they took this and they inserted a line chart. So let's throw a line chart in here and take a look at that. The average we noticed was 27.4 down here. These numbers got closer and closer to 27.4 as we did the average of them until it actually got to the number. All right, that continues. The more data you collect, the closer it's going to get. Now you'll notice it'll go up and down as you have some data going through here. You take thousands of observations, you're going to have a much more sporadic, but eventually it levels off. That's kind of the figure that they show you in 11.1. It has it all kind of leveling off eventually. All right, so that is the law of averages, law of large numbers, as you take a look at a population, and hopefully that helps you see the difference between a sample average and the mean, or mu, of a population. That's the big difference. Statistic, parameter.